Hi everyone, my name's Rachel King and I'm going to be talking to you about data analysis today. The first part of this presentation is going to be talking about data analysis, and in the second part we're going to focus on graphical representation of data. So all of you doing this course are doing some research either within your honours program or your master's program. And scientific research is founded in our curiosity to understand what and why. So we're trying to understand what relationships exist between variables, or why certain groups of things are different to other groups of things. And these what and why type questions are linked to understanding the variation that exists in the things that we're interested in. So if, for example, I was interested in the heights of students studying this course, I might want to look at the difference in heights between the males and the females. And to do that, I might measure the heights of everybody and then consider the mean of the group of males and the mean height of the group of females. But to understand if the means of these two groups are really different, we need to understand the amount of variation that exists within each group to understand the importance of the variation between the groups. So the understanding of variation is true for both quantitative and qualitative types of research. No matter what type of data we collect, we are trying to understand the variation that exists within the data. When the data is numeric or categorical, the tool we use to objectively, hopefully, assess this variation is statistics or statistical methods. We can see the fundamental importance of understanding variation in our data when we consider the most basic summary statistic that we use in statistics, which is the mean. We never give a value of the mean as a descriptor of a group or our sample without also giving a measure of the spread. So the mean represents the centre of the group of measurements, and the standard deviation is an indication of how much spread is around that mean. So if the average height of my students in this course is 170 centimetres, if I told you that the standard deviation was 10, then we would know that within 1 or 2 standard deviations above and below the mean, a large proportion of our students exist within that range. If I said the mean was 170 centimetres and the standard deviation was 20 centimetres or 30 centimetres, you get an idea, a picture in your head that the larger the standard deviation, the more spread in heights overall among the individuals. So we're taking measures of individuals, but we're trying to understand group characteristics. So using the mean as a measure of centre can be misleading unless we also accompany that mean with a measure of spread. Another measure of centre is the median, which is the middle value. If we ordered all of the values of height from lowest to highest, the median would be the middle value. And when using the median, we can use the interquartile range to give an indication of spread. We can also see the importance of variation as a statistical concept and a statistical parameter that we're trying to understand when we consider a really simple statistical test like the t-test. So the t-test is used to understand the differences between the means of two different groups. So again, if we go back to that example of heights of males and female students within who are studying this course, we are comparing the means, but the actual mathematical calculation that forms the t-test looks at the difference in means in the numerator of the fraction that explains the test, and in the denominator is a measure of the variation in the two groups. So we never consider the means without considering the variation that exists within those groups, so the variation around each mean, and then the variation between the means. So if there is more variation occurring within our groups than between our groups, then we couldn't really say the means are different. So if I had a mean of 170 centimetres for women and 175 centimetres for men, but within each group there was quite a lot of variation that overlapped, that difference of 5 centimetres wouldn't be meaningful really, because there's so much variation within the male and female group that is overlapping that difference in means is just descriptive and not due to membership within the groups. So statistics is a field of study concerned with the collection, the organisation, summarisation and analysis of data, and the drawing of inferences about a body of data when only a part of the data is observed. So when we only have a part of the whole of the data, we have a sample. I'm going to talk about inference and population and sample a bit more in a moment. So data is the raw material of statistics. For our purposes, we may define data as numbers if we're looking at quantitative statistics. So data are numbers, and numbers contain information, and the purpose of statistics is to investigate and evaluate the nature and meaning of that information. Sometimes that investigation is purely descriptive. We just will use summary statistics like means and standard deviations perhaps, or if we had categorical variables, we might just use counts or percentages. We might do some plots and represent our data graphically for descriptive purposes. Other times we want to actually use statistical methods to analyse either relationships between our variables or among our variables, or differences between groups. Generally speaking, some form of statistical analysis is needed for all forms of research, whether it's descriptive or it's actually applying statistical methods. So I mentioned a sample, using a sample just a moment ago. So why do we use a sample? Well, first let's understand what a population is. A population is a collection of all items of interest in a particular study. So a census is an example of trying to sample a whole population. It's usually expensive and often really logistically impossible. So the census is quite an easy thing to understand in terms of population, because we're thinking about human populations. But in statistics or in research, when we're talking about a population, it doesn't have to be humans. So I could be interested in the populations of a certain species of tree that exists in southeast Queensland. I could be interested in a population of small businesses that sell a certain kind of product that occur within Australia. So you as the researcher get to define your population. You get to put in place boundaries that define the extent of the different characteristics of the things you're measuring that define your population. Generally speaking, it would be very hard to sample every single member of that population, whether it's a business or a person or a tree or a mouse or whatever you're measuring. It would generally be very hard to collect data on your whole population, and you're only going to have a sample. But if that sample is a representative sample, then the variation that you are measuring in that sample reflects the variation that exists in the population. If we could collect data on a whole population, then we wouldn't need statistical methods, because the mean of a population of data is the mean. There's no uncertainty around that. We know it's exactly the mean because we've measured every single thing. When we don't have the population and we only have a sample, we know that if tomorrow we went and took another sample and measured slightly different individuals, our mean, for example, would be slightly different just because we have a different sample. But if our samples are representative of the overall variation, those means should not be too different to each other. They should be similar enough that we can use our sample as a really good example of population characteristics and variation. So the sample obviously therefore is a subset of the population, selected in a way that it represents the variation found in the whole population. And from that sample, we want to make inferences about the population based on statistical tests. So this little diagram is just to get you familiar with some of the terminology you'll often see when you're reading about statistical methods or you're trying to learn a statistical method. So we start off with our population, and from our population we're going to select a sample. And on that, based on that data in the sample, we're going to calculate certain things like a mean. And the things we calculate, the statistics we calculate on a sample, the things that describe the sample, they're statistics. So statistics in this term represents actual summary values that describe something about the sample. Now, from these statistics, we can infer parameters. So parameters are the equivalent to the statistic, but they describe the population. So the parameters are usually a little bit more uncertain. We're sure that this is the mean of this sample, and we're inferring, while allowing for a bit of uncertainty, that this parameter mean describes the population mean. Oops, I'll just go back. Sorry, moved ahead too fast. So we use different symbols to represent statistics and parameters, so that we know if we're talking about a value that represents a sample or a population. So for a mean, for example, we use X bar to represent the sample mean, and we use the symbol mu to represent the population mean. So often when you're reading about statistical methods, you'll see different symbols, and they'll both, in this case, be representing mean. One represents the sample statistic and one the population parameter. So parameter is a statistical characteristic of the population, and the population mean is usually denoted by mu. This little U symbol here is called mu. Statistic is a statistical characteristic of the sample, so the mean is X bar. Statistical inference is the procedure by which we reach a conclusion about a population on the basis of information in the sample that has been drawn from that population using probability. By that we mean that it's a random sample, a representative sample. So going from a sample to a population involves inference. These definitions allow us to classify analysis into descriptive statistics and inferential statistics. So if you calculate some summary statistics, the mean, the standard deviation, etc., of a variable that you have measured on a sample, and you are describing just your sample, then you are not doing inferential statistics, you're doing descriptive statistics. If you try to make claims about those characteristics and infer meaning in your population, then again, inferential statistics. So why should you be worried about data analysis or be concerned about data analysis? So this data on this slide is from a very old study in 1981, but it's still incredibly relevant, and it's a really good example worth using still. So papers in Marine Ecology, which is an actual journal, Marine Ecology, in 1981, Underwood looked at the number of research papers that used analysis of variance, or ANOVA. It's a specific statistical test. 151 papers were checked. 8 of those had insufficient information to properly figure out how they had performed the ANOVA, because there's different variations. 38 of them had very clear errors in the type of analysis or description. 62 out of the 151 had inappropriate analysis for the design. 51 had the analysis done incorrectly. 97 had a homogeneity of variance not tested. So homogeneity of variance is a specific assumption of the analysis of variance method. So not testing an assumption means that any results are a bit suspect. And 35 had interpretation errors. So really there was only 18 that had done a good job of explaining the method they had used, how they had applied analysis of variance and interpreted the results correctly. So only 12% of the studies were correct. So this is a pretty typical thing even today. What tends to happen is that in different disciplines, whether you're in ecology or health or any other area, IT, business, wherever your research is in, your specific discipline will adopt certain statistical methods as the norm or the way that data is generally analysed. And what that can lead to is certain methods or approaches being used that may have even just small errors in them, or things that are left out, like testing an assumption. And if that gets published in a peer-reviewed paper, then a student will come along and read that paper and quite properly think, okay, well, this is in a published article, this should be correct, I should be able to apply this same kind of analysis to my data, and I'll look at how they've done it in this journal article, and I'll try and represent my results in a similar way and follow their lead. And that's quite appropriate when you're starting out in research to do that, to look at previous research and what has been done. But if analysis or statistical methods have been performed incorrectly, then that tends to perpetuate within a discipline. So the thing I would suggest to you, not that you don't look at past research, you obviously need to do that, but don't assume that because something is in a peer-reviewed journal that it is correct. That's not how science works, actually. It's not perfect. There's never any way to stop all mistakes. What matters is that the next researcher comes along and critically reviews what has been done. Don't take anything as truth. You should always be critically assessing previous work before you try and apply similar approaches to your own work. That's really hard when you're first starting out in research and you have to rely on your supervisors to help advise you in that. I don't want this to seem too daunting, but just to make you aware that just because something is in a published journal article does not make it perfect. There still could be errors. So this graph is from Glance in 1987, another really old example, but again, a good one, I think. So this is the percentage of papers with errors, 1950, 60, 70, and 80. So this is the percentage with a standard deviation applied here. I'm actually showing this graph because in the next part of this presentation, I'm going to be talking to you about graphs and good graphs and bad graphs. And so I'm going to come back to this example because there's a couple of errors on this graph that I think we'll come back to it and have a look at it at the end. So in this one, again from Glance in 1987 in Circulation, which is a particular journal, Circulation, and volume 56 of this journal, we've got the percentage of papers that had no statistical analysis, appropriate t-tests, appropriate use of ANOVAs, appropriate use of other tests, incorrect use of t-tests. So again, we might come back to this one. I think it's interesting to look at these percentages. Less than 25% had appropriate use of t-tests, and I would say that's less than 5% had appropriate use of ANOVAs. So the data here itself is of interest to what we're talking about at the moment, but this is another graph I'm going to come back to at the end because there are some mistakes on it that could lead to misinterpretation of this data. But finally, I just wanted to make it clear that really use previous examples, but read widely. Don't necessarily only read in your own discipline. I don't mean you need to go and read from a statistical journal or anything like that, but try and read a bit more widely than your own discipline to get ideas from other areas, see how things are being used. If it's vastly different to how your discipline applies a certain method, maybe you can start a discussion about that with other students or your supervisor and try and figure out which would be the best approach. So I just want to clarify this one thing that makes no sense in statistics. In statistics, the precision of language is crucial to avoid misuse or misunderstanding of findings and for replication of methods and results. In statistics, we don't want to overstate our results. We are very cautious about making claims unless the data strongly backs those claims. So language is incredibly important in that context. Yet the problem is there's real inconsistency in the use of language around statistical methods and application of statistics when you look across disciplines. There's no solution to this. It arises from the fact that, as I said, each discipline tends to use certain methods consistently or a lot in their field, and the language within the discipline starts to evolve. And so how ANOVAs are explained and referred to in biology might be a bit different to how that occurs in business. And different types of words are used to describe the components of the analysis. Unfortunately, as I said, there's no clear answer to this. It can be frustrating and it can be a real barrier when you're first trying to understand statistics. So my advice here would be that if you are getting confused by some of the language, maybe just take comfort in the fact that it's not you. There is a real problem here with inconsistency of language within statistics. So just try and keep going. Don't let it stop you from progressing, because improving your skills in the area of data analysis and statistics, if you're interested in research, will always be a great advantage. So it's worth pursuing. Just some simple examples. So quantitative, when we refer to quantitative data, that's often referred to as numeric or continuous or scale or interval or ratio or ordinal or nominal data. So interval, ratio, ordinal and nominal data are not all the same thing, but all of them are quantitative. So it can get a little bit confusing. Qualitative can be character or categorical or ordinal and nominal. Again, ordinal and nominal can be quantitative, but they can also be qualitative. An independent variable can be called an explanatory variable or a factor or a regressor, a dummy, a control, or an input variable. And a dependent variable can be a response and outcome or the explained variable. So within tests, different software can use different output names, different names to refer to similar concepts or processes or choices or outputs. So SPSS may refer to certain aspects they may call independent and dependent variables, where SAS may want the response variable. So different software can also compound the issue around language. So we can think of types of research in terms of data collection. Experimental research is where the treatment or the manipulation is imposed on individuals randomly to observe their responses. So we might be looking at DPI plant trials, where we give some plants a fertilizer and some plants not receive the fertilizer. So we, the researcher, are imposing a manipulation on the things we are measuring. Or drug trials, where we have some people receiving a placebo and some receiving medication. And so that's an experimental type of research, because how we're collecting the data, how we're measuring effect, is by imposing certain conditions on some people within our sample, or some cases, not necessarily people. So observational research occurs when the manipulation occurs naturally rather than being imposed by the researcher. So observational study may be looking at the difference in lung capacity of smokers or non-smokers. So we're still looking at a medical situation, and we may have a control group by looking at non-smokers as well as smokers. But we can't choose people and tell them to smoke. We have to, the people we put into the smoker group have to be people who are already smoking. So it's a condition that is naturally, in quotation marks, naturally occurring. The researcher does not control or randomly allocate the treatment to the people in the study. We're going to discuss the difference between experimental and observational studies quite a bit more in the next module that we look at, called experimental design. So not in this recording, in the next recording. So that's all I'm going to talk about today on research, approaches to research, and what is statistics. So for the rest of this recording, we're going to look at graphing and what constitutes a good and a bad graph, and some things you need to think about. We all want to put plots into our results because they're a great way of describing what we want to describe, tell our story. But there's ways that we can really mislead our reader or whoever we're presenting our research to, and we may not mean to do it. So I'm just going to highlight a few things in the next, in the rest of this recording. So the reason we use data visualization is for exploration and for explanation. So the first is exploration, when we get our data and we're sitting at our computer and we're trying to figure out the story of our data, see what it all says, what were actually the results of all these measurements we took. And in that process, you can do anything you want. It doesn't matter which plot you build. It doesn't matter if you make mistakes, because it's just between you and your computer at that stage. There's no wrong thing to do when you're exploring. Once I go through all the points of this presentation, you'll see that there actually are some wrong things you can do in creating data. So the only wrong thing you do in the exploration stage is that you may waste time by going down paths you shouldn't have gone. So hopefully by taking in some of the information I'm presenting here, that might stop that. But there's nothing, you shouldn't hesitate in trying things. There's no harm in trying something. If it doesn't work, it doesn't work. No one's harmed, no one's injured. Your data hasn't been damaged, it's still in the same state it always was. You may just have wasted a morning making some graphs that you don't end up using, but it will still help you understand your data. So I don't really think it's wasted time. So the second reason we use graphs is for explanation. So that's to tell the story of our data to an audience. And at that point, it really is critical to think about some of the things I'm going to discuss for the rest of this presentation, so that you don't mislead your audience in any way. So we use graphs to summarize complex data into its simplest understandable form. We often have large amounts of data and we want to focus on a particular aspect and present that. So one of the things that is quite common when people read a graph is that we have an assumption that a graph should be easy. So we tend to gloss over it, and we're used to seeing graphs in advertising and marketing, and they're flashy, and we just look at them quickly and we take home the message really quickly. We understand what they're trying to tell us really quickly, and that's all there is to it. But when it comes to research, the graphs are often much more complex, and even if it's a simple looking graph, it's still trying to summarize probably quite a lot of information. So it's important that we don't treat them superficially, that we really take the time to look at a graph and make sure we understand it. The first thing to always do when you're reading someone else's graph is to make sure you understand what is on the x-axis, what is on the y-axis. Make sure you understand what those things measure before you look into the center of the graph and try and take home the message of the graph. If you just look at the center and don't take the time to really read what's on the x and y axis, you can inadvertently misinterpret what is being said, and then it's hard to go back and relearn what you were supposed to understand the first time round. So I mentioned advertising. So this is just, I think we can learn a lot about the history of advertising and how graphs are used to understand how they're often misused. So in the 1950s, advertising was predominantly long copy. So what that means is in the newspaper, a whole page was filled with just paragraphs of words where the business or the company or the marketing were trying to convince the consumer to buy their product, and they would basically write an essay and fill up a page with just paragraphs of writing that had an argument of why their product was the best. And then in the 1960s, the advertising world understood the power of visualizations. They understood that pictures circumvent the consumer's critical thought. Visuals are registered before you have had time to analyze them, so they become the truth in your head even when they're not. That's really powerful. Pictures circumvent consumers' critical thought. So we don't flip a switch when we go from our everyday life seeing pictures and advertising and graphs and plots thrown at us to when we're looking at a research paper. There's nothing in our brain that says, oh no, read this graph differently. So again, if we take home straight away the wrong information because the graph is a bit misleading visually, then it's really, really hard to change our minds. No matter how much argument there is in the rest of the paper, if we look at a figure or a graph and it's misleading, it's very hard to learn the truth later on. It's hard to change our minds. So let's talk about some rules for data visualization. If you were to Google rules for graphs or rules for data visualization, you'd come up with a ton of different websites telling you what the rules are. I think there are some things that are actual rules. There are some things that you just should not do ever. There are some things that should be rules, but there are some things that can be broken depending on the circumstances. Not everything applies all the time. But what we need to consider is if any of these rules, in quotation marks, if they are broken, does it lead to our graph being misleading in any way? So looking at this table, we can see that if we have one single variable and it's a categorical variable, then we should use a bar graph to display this data. So a bar graph has along the x-axis it would have categories and the y-axis would be counts or percentages. But the important thing in a bar graph is that the bars do not touch. There's a gap between them because these are categories of things. They're discrete units of things. They're not a continuum. If we had a single variable and it was quantitative, so this might be height, this one that was categorical, that may be hair colour, brown, red, black, and this is the percentage of people with that hair colour. This would be a quantitative variable, so say height, and we can use a histogram. So because height along the x-axis is a continuous variable, the bars are joined together in a continuum. So we're grouping them into smaller groups so we can get the frequency or the counts within each range group of each bin, but we join them together because it is a continuous variable. We could also use a box plot. So in this case, height would be on the y-axis. So this is the median height here, this is the maximum, and this is the minimum. If we had two categorical variables, a categorical and a categorical, we could use a stacked bar graph. So that would be like this one, but if we had hair colour again, and we were looking at males and females, we may have, this bar divided into green and red for males and females, and same with this bar, green and red, divide them up. A clustered bar graph would be similar to this, but we would have a bar for males and a bar for females in this category, then a bar for males and a bar for females in this category, etc. And we can have totals or counts, or we can have conditional counts. So it totally depends on how what interest you have. If we had a categorical variable and a quantitative variable, we could use side-by-side histograms like these two here. So this might be males and females, and then we would have height along the x-axis here. So, height along the y-axis here, and this is frequency of males and females along those heights. If we had a quantitative variable and a quantitative variable, so two quantitative variables here, we might have a scatter plot. So we'd have height and weight, for example, and then for each individual, their height and weight. So each point on this plot is a different individual. Just going back to this one here, we had a categorical and a quantitative. We could have heights based on different age groups, so child, adult, elderly, or something like that. And this again would be, the categorical variable would be along the x-axis here, and height would be on the y-axis. So these are actual rules. It depends on the type of data you have will determine the correct type of graph that you can use. So if you have a quantitative variable, you should not be using a bar chart, you should be using a histogram. There's no changing that rule, that's just the way it is. If you use the wrong type of graph for the type of data, you're making a fundamental flaw. So I think that is a firm rule. Within each of those groups, there are options like box plots or histograms, etc. So you need to consider your audience. Are you preparing these results for a journal, for a conference presentation or a poster, or for, say, the journal, the conversation, which is written for a more general audience rather than a scientific audience? Also remember, specifically for a conference presentation or a journal article, the types of figures you create can be really different. One, you need to think about colour. Two, just complexity. You can often get away with more complexity in a plot in a conference presentation when you are actually describing it in person during the presentation, and you can point to different things. But in a journal article that's static and just two-dimensional on a page, you may have to change the kind of presentational graph that you're putting together. So this is an example of problems with colour. So one, the black background. This is actually a plot from Joanna Turner. This is one of hers that we messed around with to make some mistakes. I want to bring up the problem of colour blindness. If you are giving a presentation, it's really tempting to do lots of nice colours. But you must remember in any presentation that there'll be people in your audience that are red, green or blue, yellow colourblind. So be really careful about that. One of the good things Joanna has on this graph is that she's got different shapes and colours. So at least in a presentation you can say the red circles or the blue triangles or something like that for those people who may not be able to see the colours you have used. But make sure your key matches your actual plot. So here she's got red associated with the blue and green with the red, etc. So you need to be really careful when you're adding that level of complexity to your plot that you are consistent. So some more actual rules, I think. Before you finalise any plot, check your data, go back and check any weird looking outliers or spikes or dips. Make sure your axes are labelled with variable names and that you have units on your axes. So, and if you're giving a percentage of something, make sure you give the sample size as well. 10% of 30 is very different to 10% of 300 in how I would interpret that graph. So it's really important that you never give a percentage value without somewhere on the plot alerting the reader to what the sample size is, what the percentage of how many. If you need a legend or a figure caption, make sure you include coding, symbols, colouring and units. And also we need to remember that it is almost impossible for a reader to verify your data. In the age of big data and online journals, some journals are moving towards asking authors to submit their data with their paper to make it available to a reader, but that's still not the norm. It's happening sometimes and it's increasing, and that's a good thing, but it's certainly not the norm yet. So you have to have integrity about what you're presenting. The reader has to trust you that you are telling the truth without having the opportunity to go back to the original data. So if you've checked your data and you're sure it's all good and everything's all right, how could accurate data produce a misleading graph? Well, there's unintentional bias, and that can come from distortion of scale and perspective, and we'll look at some examples in a moment. There's inappropriate choice of graph, so if you just choose the wrong type of graph for your type of data, you could unintentionally cause bias in how your graph will be interpreted. And often, as researchers, we're intimately familiar with the data and its subtleties, and we take them for granted. So it's always good to make sure someone else is reviewing your work. At the point you get to putting your graphs together, you often forget some of the really basic things that you didn't even know at the start, but now you're so familiar with that you just forget to mention them. So having someone else check your work is really important. Then there's intentional misuse of data, and that can be done through distortion of scale and perspective as well. That can be used as a tool to intentionally misuse and misinform and mislead. And also, one good way to have a look at whether a graph is being used to intentionally mislead you is to look at the accompanying text and see the intent of the author. Are they just picking one story to tell when it's very clear there's other stories in the data and they've got their own bias that is reflected in the text? The biggest intentional misuse is overinterpretation of results, which happens quite a lot in advertising and marketing and also in politics. So you'll have very small sample sizes, and you'll have authors or the text around the graph will be claiming things that really the data is not fit to justify those claims. So Ed Tufte from Yale University came up with the idea of the lie factor as a measure of the amount of distortion in a graph. So basically his idea was that the size of the effect shown in the graph compared to the size of the effect shown in data. So when we're talking about size of effect, you can think about this in terms of the difference between the heights of two bars on a graph. If we're claiming that these two categories of things are really different from each other because the counts or the number, the frequency of individuals within each group is very different. So if that size of effect in the data is not the same as the size of effect shown in the graph, then there's a lie factor. So if this equation equals 1, so these two effect sizes are the same, and this equals 1, then the graph is not exaggerating anything, it's doing a good job. But if it is larger than 1, then the effect in the data would be smaller than the effect in the graph. So the graph is overemphasizing the effect, so that then is a lie factor, which is something you need to worry about. If your effect on the graph is smaller than that shown in data, that can also be a problem too if someone's trying to hide something. So if it's either larger than 1 or smaller than 1, you should probably explore. So this is a paper by Cooper. It's in the papers that are available on the study desk in the data analysis and experimental design block. So this is one where they looked at 85 scientific graphs in 63 distinct advertisements. 36% of the graphs contain sufficient information. 36% is not a great result for correct graphs. 91% of the graphs defined all the abbreviations, so that's good. 55% had a title, which is good. 78% had clear quantitative labels for the X and Y dimensions. I'm not sure 78% is something to be happy about, though. I think it should be much higher than that. 53% had a figure legend and 69% depicted the sample size. That's a really big problem, that only 69% depicted the sample size on a graph. So these graphs were pharmaceutical ads in a scientific journal. So these are graphs that GPs and other doctors are seeing from pharmaceutical companies advertising their products. People in the medical field are no better than the general person at interpreting graphs. So I think this kind of thing is a real cause for concern. We can't do much about these advertisers in these medical journals, but we can make sure that any graphs we publish are not distorting the effects in any way. So we're just going to work through a few graphs about how graphs mislead. So in this first one here, you can see if we just straight away look at this graph, it looks like A is much, much smaller than C. And if we don't look any further, that's the truth that we would take away from this graph. And it's only when we stop and we start looking at the axes that we can see that perhaps we're being misled by this graph. So it looks like Group C is at least 4 times the size of Group A. So that would be a lie factor of 16. This is that same data, the exact same data plotted without the 3D distortion and with the y-axis starting at 0. And you can see that there really is not that much difference between the 3 categories. I've just given them labels here, but it is exactly the same data. So the walk-away impression from this graph is vastly different to what you would walk away from this graph if you just quickly looked at it and didn't really look at the detail. But even if you took into account the change in the y-axis here, starting from 4 and only going to 6, this 3D effect, it looks pretty and it looks nice and it's very tempting to do for graphs, but the human brain is not very good at assessing height and volume or area all at the same time. So when we're looking at volume, the human brain tends to overemphasize. So this volume effect here makes our interpretation of the different heights even more exaggerated. So you should never use this 3D effect on any scientific graphs. There is no need for it. It looks pretty, I know, but it does not help the reader in any way. In fact, it distorts their interpretation. So on this graph, I've started at 0. It's not always appropriate to start at 0. So if you had the data you were plotting, you were doing a scatter plot, for example, and you didn't have values starting until 4 or above, you wouldn't want all this empty space at the bottom. So that may be justified not starting at 0, but you would want to make sure you draw the reader's attention to that. You can put a little Z at the start here to indicate that you're not starting at 0, a little dotted Z line, and you can refer to it in your caption to draw the reader's attention to the fact. The other thing to think about is the use of grid lines. I've used quite a few here. I may possibly have overused them in this plot here. Maybe I only needed them at 2, 4 and 6. It could be that this number of grid lines is just making it a bit too busy and distracting. But that's, again, just a choice that needs to be made. So here we're going to look at how percentages are used. So in this graph here we have the frequency of pass grades. So this is the frequency or the number of males that passed and the numbers of females that passed. Now, maybe this is a certain test or an exam. So if I was to plot the percentages here, you need to be really clear about what your sample size is, what you're calculating that percentage on. So here I have calculated the percentage of males out of the total number of students, 45. So that's not the number of students who passed, that's the total number of students who sat the test. So it's the percentage of males out of the total and the percentage of females out of the total. Another way I could plot this is to say there were 22 males who passed and 25 males who sat the exam. So this is the proportion of males out of the who passed out of the total number of males who sat the exam. And this is the proportion of females who passed out of the total number of females who sat the exam. So you can see how these bars look quite different. The heights, females are lower here, very slightly higher here. And unless you're very clear about what this percentage represents, it can be very easily misinterpreted. So you need to make it clear to the reader what this percentage is out of. So it's 82% of what? In this case, 25. So this data I'm going to show you now is some data that's available in the R statistical package. It's on the deaths of people who are on the Titanic. And what I want to do is talk to you about scale. So this is what we call a panel plot. So here we have any graph in any plot here is about male children. This is female children, male adults and female adults. And blue is that they did not survive and pink is that they did survive. So when we look at this data here, we have kept the exact same scale for each panel. But the problem is that there were way fewer children on the Titanic than there were adults. So these bars here get squished right down because in total there were fewer children on the Titanic. So we can't really see what is going on in here when we use exactly the same scale. This first row here is crew. There were no children in the crew, so there's no bars here. And then we have first, second and third class. So what we can do is think about what do we really want to tell. If the story we want to tell is we're not interested in the subtleties within each of these bars here, we want it very clear that there was fewer children overall, then keeping the same scale is the best thing to do. But what we can do is change the scale for the children to be smaller overall so that these bars stretch out. And all we have to do then is make sure it's really clear to the reader. So something I could have done here perhaps was colour code this scale a different colour to these ones here, so that the reader would catch that and they'd go, oh, why have these been coloured differently? And I could explain it in the figure caption perhaps. But again, it's not that this one's right and this one's wrong. What we have to think about is, I've decided this is how I want to present my data. What I then have to think about is, how could this be misinterpreted? What do I need to make very clear to the reader to make sure they don't walk away with the wrong impression? And how can I do that? So the first thing I would think about is changing the colour perhaps of these two scales. The other thing is you could actually split this. Just don't plot them in 4 panels. Plot these two together and have that as one figure and then this as another figure, and then the reader is less likely to assume the same scale. So in this graph here, when we first look at this, it really looks like the biggest difference here is between category A and B. But when we look a bit closer, we can see that these y-axis increments are not linear, so we're going 1, 2, 4, 8 and 16. So if I change that scale back to equal increments, we can see that the biggest change is actually between C and D. Now, maybe I had transformed the data in some way that I actually need to use this scale. This was correct and this is incorrect. Perhaps maybe this is misleading. But unless I make it really clear by my axis label, then it's very easy for someone to misinterpret. The other thing is that because we have categories along our x-axis, we should never use a line. There's nothing joining A and B. They are discrete groups from each other and they should not be joined together by a line. We should use either just dots or bars to indicate that these are discrete groups. So this was a plot that was published in the Nature journal, which is a very good journal. It's to do with astronomy, looking at radial velocity data. And so they're expecting a regular repeating curve here. So they know what they're looking for here. What they don't know is the period, so how wide between the peaks. And that's what they're trying to fit to this data. So on this data, they've, put in the error bars and everything, and they've, put this red line through. But really, it's hard to see how that line was fit at all. If we know they're looking for a regular sequence, then that sort of explains some of this fit. The rest of it really is driven by this void here and this small void here, which has pulled these up here, and also this bit is a little bit sparser, which is pulling this down here. Now, astronomy data is always noisy. There's no way around that. And they do the best they can, and they've tried to explain really, really deeply here why this is a good curve. I think there's some things they could have done to this graph that would have made it seem less definitive. Like maybe using a dotted line through here would have been a better approach, because really, just looking at this, I sort of question it straight away. So I think they've sort of tried to claim a level of certainty that probably doesn't exist. This graph represents a real misunderstanding of a method that has been used. Regression has been used there. They've had the dots in blue and red, the winning 100-metre sprint times for men and for women in red and men in blue, and they've fit a linear regression to that data and got the slope. Now, one of the conditions of linear regression is that you can interpolate, you can fit that line, and then I could predict the winning times anywhere within that range. But extrapolating is very dangerous, and you can see why. They've just straight line extrapolated out here, and so now they're claiming that in 22:52 women will have winning times of just over 6 seconds, which seems a bit ridiculous. So we don't know what's going to happen to this relationship beyond the point that we have measured data. I would imagine that it's going to flatten out for both men and women. We can't keep going until, if this kept going, if they kept extrapolating this out, why did they stop it this year? Keep extrapolating and you'll get to, 1 second. So it becomes a bit ridiculous after a certain point. So this is an actual published journal article, and it was also published in Nature. So it's a bit concerning when some of these graphs get through peer review. So in this one, we want to look at the headline first. Why the drop in illegal movie downloads in Australia? So the headline is telling you that we're talking about a drop. Something has decreased. And then we go to the graph and we see, oh, look at this decrease. That looks really steep. Look at that steep decrease. But then when we look at the graph more closely, we can see that the actual drop is between the two lines. This is 2014 and 2015, and they're claimed these are age groups of people. So this drop here is meaningless. These are categories, age groups. They should not be joined by a line. The drop they're claiming up here is the difference between, from 2014, it's dropped a little bit for this age group, and for this age group, no drop here and a bit of a drop here. So this graph really is misleading. They're talking about a drop and they've graphed it in a way that shows a decrease that your eye is attracted to. They've kept the scale at a scale that shows you quite a steep decrease. So even if before even reading anymore, you are expecting that there's been something really quite dramatic has happened here. This is another one of Joanna's plots, and I'm using it to show why in some cases you need to transform your data, so in this case using a log scale with weighted and unweighted data, and why you may need to do that when you want to compare things directly on a graph. So if we look at this one and then we look at this exact same data here with this one not transformed, it becomes impossible to tell your story if you don't actually perform this transformation, which is a normal thing done with UV data. It's well accepted in the field. And this is what Jo should be doing with her data. But what you need to do is make sure, if you were presenting this at a public talk or you were presenting it even at a presentation where not everyone is familiar with your area of research, you need to make sure you explain it as Jo has done here. She's made sure she's got the scale and the units here, and that in her key here she's got solar output and weighted solar output, and in her caption she would explain what she's done as well. So this one here, we look at this and it looks like 2011 is higher than any other year, and that's because of this perspective. So just before I was mentioning that human brains aren't great at discerning the difference between volumes or areas rather than just heights. This is combining that problem with a perspective problem as well. So the thing further away is going to look shorter. Plus we've got no y-axis scale to even try and visualize what's going on here. So if I replot this data just in a flat, boring old plot, we can see that these 2 years are exactly the same. So this is misleading, intentional or not. People would look at this graph and take away an incorrect interpretation. So this one isn't as pretty, it's not as attractive, but it's more truthful. So here we're going to look at a pie chart. As a statistician, I have to preface this by saying please never use pie charts. I know some of you will, but as statisticians, we really don't like them. One of the reasons is this area problem again. If we're looking at the area of a bar, human brains are pretty good because there's straight lines, we can judge that area difference. When you're looking at a pie chart, because we've got a curved line and then we've got these angular lines, it distorts our perspective and our judgment of area. So if you have a pie chart that has only 2 or 3 pieces, that's not too bad. But once you start getting down to smaller pieces, the difference between this one and even this one, we're not judging really the relational differences that we're trying to evaluate. just aren't as clear as they should be. And in this graph, we're trying to comprehend area, percentages, and different colours. The easiest thing to do here would just simply be do a bar graph that we could order in size. So we could rank basically our countries. So we can say Canada is the smallest at 5% and just go down to Australia at 36%. It is a much better approach. There's no misinterpretation here. Your audience is going to understand what your data is saying much more quickly, and this is just a bit too confusing. Yes, so pie charts are used to show the relationship between parts of a whole, and with these circular and then angular lines, we tend to misjudge those proportions, even with the percentages labelled there. So if you have a few moments and want to Google bad correlations, there's a ton of websites out there that have all these bad correlations. So when we're talking about correlation, we're talking about comparing values of one variable to another variable. So we've measured two things, so age and height perhaps, or weight and height. We've measured the same two things on lots of different people, and we want to look at the relationship. And this is saying that because these two variables have similar patterns, therefore one causes the other. The main point of these graphs is to highlight that correlation, finding a relationship between two variables, so a positive linear relationship which indicates as one increases, the other increases. That's just a relationship, it's not causal. You can't claim one causes the other just because you see a pattern in the relationship there. So this one is looking at the average global temperature and the National Science Foundation Research and Development Fund. So basically, is global warming a hoax propagated by scientists? As the funding for the R&D budget increased, average temperatures increased. So therefore, if we reduced funding to R&D, global warming wouldn't be a problem if one caused the other. This one is murders in New York State, and this mountain range has the same shape as the rate of murders in New York State. Therefore, they must be related, and the mountain must be causing the murders. No, they just happen to have a similar distribution, that's all. This is a really good example of a bad pie chart. This is back in 2012 when American politics was dominated by Sarah Palin. And this is saying that 70% of GOP candidates backed Palin, 60% Romney, and 63% Huckabee. I'm not sure how this adds up to 100%. Oops. I'm not sure how this adds up to 100% at all, and this is the type of political plot that is intentionally misleading, I'm sure. It's becoming more and more common to see pictographs used in graphs instead of just doing a bar. They want to put a picture of the thing that they're studying. The problem here again is one of volume and area and size, and that it's hard for us to focus just on the fact that this is 150 and this is 300. This looks way more than twice the size of this one, and we overinterpret the volume. So if we do that, again, we've still got area to consider. So we should have the same width of bars. It looks pretty and it's eye-catching, but it's really not doing yourself any favours in making sure that you're not misinterpreting your data. The other thing is with a pie chart, again, or any kind of chart where you're talking about percentages, to make sure you talk about how many. So is, in this case, 23%, is it 81 or is it 15? Depends what your total is. So never give a percentage without saying what the overall sample size is. This iPhone one here, this is the plot of that just as a dot point. And it's far less misleading than even this one, let alone the 3D version. So some things I think should be rules are you should only ever have a 2D plot. Never put fake 3D dimensions onto a plot. Don't distort perspective. Check that you've not exaggerated effect size. Again, I put a vote out there for no pie charts if you can help it. There's always a better chart to pick than a pie chart. Summarize complex data into its simplest understandable form. That's the job of a graph. If you can't do that, if your graph is so convoluted, then you need to stop and think about whether you should be splitting this up. Split it up into two graphs. It's a way to tell your story better than trying to cram everything into one plot. And only use lines to join points if continuous data is being used. and leave gaps for missing data. Some suggestions. I think you should try setting your y-axis to start at 0, and if it doesn't work, if you've got a great big heap of empty space there, then don't, but make sure you draw attention to the fact that it's not starting at 0. Don't forget colour blindness. 1 in 12 men are colour blind, especially if you're doing a conference presentation. Avoid patterns, lines and borders of bars as different colours. Don't try and get fancy. It's nice, it's always tempting to try and make your graph look pretty, but it's not helping tell your story. It's not adding anything. It's probably drawing away from what the actual data and the information you're trying to convey. You need to think about whether your graph will convert from colour to grayscale. So in some journals you can pay to have colour figures in your journal article, others not. So you need to think about whether you want to be using colour or not. Don't overdo tick marks or grid lines. In one of those examples I mentioned the fact that I probably used too many grid lines. So you want to make sure you use enough that people can interpret your data without, having really wide gaps. But don't overdo it. Be consistent in your use of scales on multiple plots. Do you need one graph or two or more to express your data? And can your data be adequately expressed just in one graph? So captions explain a graph in 2 sentences or less. You'll remember that nature graph, the graph from nature for the astronomy data, needed, great big paragraph to try and explain the plot. That seems like they may have reconsidered their approach there. Does your plot stand alone? So you've got interpretable axes and legends and units on there, sample size. Is everything on your plot that is needed without the reader having to search through the text of your article to figure out what the heck is going on? I'll just skip back now. Now that we've talked about all these graphs, I'm just going to skip back to those earlier graphs I said I was going to come back to, just to discuss some of the things I think are really a problem with these graphs. If I can find them. Here we go. So this one here, if we look, we've got percent of papers with errors, so 60% or around 50%, but I have no idea really 60% of what. Was there the same number of articles in 1950 as there were in 1960? Is this 60% of 100 and this is 50% of 500? I have no idea of what these percentages really represent. If this is 60% of the total number of articles or the number of articles in 1950, I'm not sure. So that's a real problem, I think. Giving percentages without the sample size is definitely a rule. Never ever do that. On this one here, again, we've got percentages and we're not really sure of what. The other thing is it's the number appropriate times the percentage that t-tests were used in an appropriate way, but I don't know how many times it wasn't. It's a really confusing kind of graph. The other thing, I think this is a good example of maybe not enough tick marks because we've gone from 0 to 25 to 50. It might have been really helpful to have a few smaller increments here, so that would have let me interpret ANOVA a bit better. It's hard for me to figure out what that height is there. So these tick marks, if there'd been a few additional ones within, so if it had gone up by 10 instead of 25, that might have been really helpful. Okay, so that's all I have for this recording. I'll see you in the experimental design one.